see who knows what. All right, so quickly, we have speed and velocity. What's the difference between speed and velocity, Sammy? Good. Okay. So, speed, how fast, and velocity is speed with a direction. Okay, so and then we say that the velocity is a vector function because remember, again, it has magnitude and direction. Speed is not a vector function. We'll continue to get into exactly what we mean by vector functions as we go, but when you include that direction, speed goes from speed to velocity, right? So, how far can a person run in 15 minutes if they run at an average speed of 16 kilometers per hour? Anybody have a good answer for that?
Was this the whole one?
And the problem of the day? Yeah.
4 kilometers.
4 kilometers? Now, how did he do that? Go ahead, Mr. Costello. Good. So 15 minutes is 0.25 hours. And if you go 16 kilometers an hour, 0.25 of 16 is 4 kilometers. All right. And looking at the formula, remember speed is distance divided by time, right? So if you solve for distance, you have speed multiplied by time is equal to distance. And then you plug it in from there and you're good. All right. Okay. So a snail can move approximately 0.3 meters per minute. Okay. Now that sounds like a speed to me, right? How many meters can a snail travel in 15 minutes? All right. So we are trying to find the distance, right? Because it says how many meters. So again, we're going to use the same setup. Speed multiplied by time is equal to distance. So if we put in 0.3 meters per minute, and the time is 15 minutes. Right? So then when you multiply that out, cancel minutes, what do you get? 4.5. Okay, 4.5 meters. Any questions on that? Okay, now, before we go on to notes, let's take a quick look at the homework. Make sure you guys are good on this. Anything that you had problems with on that? First thing I'll say is, that's a nice simple question, but it's an extremely important one that you understand the answer to. What does per mean?
Per mean?
Yeah.
Like and?
What?
Like and?
Like per hour, right? It's division. Thank you. Every time you see the per, either the units are going to be divided or you're going to have to divide something. As soon as you see per, think division. Just make that connection in your brain, and life will be easier for you. For some reason, I'm just not able to spell today. Is that right? No, or whatever. All right, so any of these other ones that gave you any kind of issue, any problem? Pretty straightforward stuff, right? Okay, good. So, given next Thursday, because that's good, that I have to make sure that I remind you of my inspiration. My inspiration was for next Thursday, and you guys are going to have your next quiz. So, if you have those situations just like that on the quiz on Thursday, everyone is going to be in good shape.
Yes.
100%, no problem, right?
Yes.
All right? All right, good. I'm looking forward to it. Before we move on, any questions for this? Going once, twice? Okay. You have in your class notes some new notes.
Acceleration notes.
All right. You have speed graphs. Okay. Everyone should be excited. We get to go to graphs now because graphs are fun. We love graphs. We love graphs in physical science. All right. Put your phone away there, Isaac. I guess I shouldn't say that on the video. That's all right. Anna and Marissa and Madison and Ella won't be surprised. I'm reminding myself of who they are. Okay, so distance versus time graph. So now we have an idea of what speed means and velocity and what motion means, right? What causes motion? That lack of equilibrium in the system. And now we need to represent it visually, okay? And we're going to do this with distance versus time graphs. And just like our density graphs, we're going to do these in a very specific way, right? So speed is the distance an object travels per unit of time, right? So basically what happens when people set these things up is they'll take any given situation, right? So let's say we have somebody who is walking down a hall here, or walking down I guess it would be a really long hall, be 100 meters. And we'll say, okay, every so many seconds, we're going to see how far they traveled, what distance they traveled. Now it's the speed, so we're talking distance, right? We're gonna have to help Isaac out a lot today. Keep working on it. Okay. So when you pick some general point of time that you're going to continually take points on, and at that point of time, maybe you have a camera or something, and then you can judge how far that person has moved or that object has moved in that amount of time. All right. Just like you see here. Say, okay, in 50 seconds, then it goes 50 meters. In 100 seconds, it goes 100 meters. All right. Now, we can start to take those points and put them onto a graph. Okay. So this time is always plotted on the x-axis. So that means that time is the which variable? The independent or dependent? Independent, right? All right. Now that makes sense because if, let's say, we used Liz yesterday, we'll keep using Liz today. Let's say if we have Liz walking down the hall to the office or something, how fast Liz walks is up to Liz. I mean, we don't, as experimenters, if we're observing Liz's behavior, we don't control how fast Liz walks. Okay? What?
What have you done to the office?
You have to pick up Isaac's medication. How's that? Open him out. Okay? No. That's not our scandal. All right? Now, but regardless of it, we don't control how fast Liz walks, right? But we can control how often we take measurements, right? That's why time is the independent variable. Because we pick how often we want to take time. And depending upon, how good your equipment is, you can do it in like fractions of a second and then just do every little spot along the way. And the more of those you do, the better readings you're going to get, the better data you're going to get. That doesn't matter. Still, as the investigator, you would pick the time, right? You can't really pick the distance on how far something's going to travel, right? And then have the time figured out later. I mean, that would be really hard to do, right? That's not going to be a very convenient experiment, right? So it's going to be the same way we did before, where you have the independent on the X, obviously, and the dependent on the Y, but you're going to put the units in there and all that good stuff, just like you did before. That part is not changing, right? So now, another thing to think about here, and I always forget, do I hit this, is the origin, right? The 0 time, remember, that's not 0 time. That's just when we start keeping track of time, right? 0 time would be like, the beginning of the universe or whatever. But it's not an objective measurement. It's subjective. It's up to us. So whenever we start the experiment, that's when 0 time is. And you have to keep that in mind. And typically speaking, it's also going to be 0 distance. Doesn't have to be, right? But you're going to try to take it that way, right? Because if we have this happen right now and Liz gets up and goes, then right here would be our 0 distance. Right?
Yeah.
That would make the most sense.
Yeah.
Okay? So, or wherever she was when she was told to do it. Okay? So, time on the X, distance on the Y. All right? Okay? Now, what's going to be one of the things that you're going to need to be able to do is just to look at general lines here of distance versus time and say, okay, what is this object doing? All right? Now, if you have this flat line and if the distance is not changing, what does that tell us? Stop, right? So if we started right now and we kept going here and we had Liz sitting here, this would be like that graph right there. Right? Because this is the starting point, and she's not moving anywhere from that starting point. Okay? So that's the way this would look, because she right now is at rest. Right? All right, but through the way there, not lunchtime. Now, okay? So if you have this nice, pretty constant slope, that means that the amount of distance is changing in a very steady fashion. In other words, it's a constant speed. All right? So this means, again, if we are studying Liz going down to the office, it means she's not speeding up, she's not slowing down, she's just walking at her pace.
Yeah.
Right? Whatever pace it is, she's not changing it. Right? So if that's the case, then you're going to have a nice constant slope. Now, again, we're keeping a close eye on these lines, right? And this is how it would look if she had a constant speed, if we decided to do, every second, in this case, it'd be every 10 seconds, whatever. If she didn't change, that means that for all those intervals, whatever the distance that she moves is not going to change. Yes? Just do a pass. Oh. That makes it hard to do a pass. Okay. So, we have a constant graph, and then this means a positive slope. All right? Positive slope means that she's constantly moving, that she's moving at a constant rate away from the starting point. Shh. What's wrong, guys? Everything's going crazy today. Okay. Now, here's an important possibility. Let's say we have 2 trials with Liz.
Oh.
What's the difference between these 2 trials?
One's farther.
Right? So for this one, she's moving like this. How is this movement different?
Faster.
Faster, right?
We're going to the opposite.
Right. So maybe in one case, she walks down there. In the other case, she just jogs down. So this would be like Liz jogging. Right? So the slope of this, by the way, let's think about this. All right, guys. Sit down, relax.
I was just trying to make sure I saw it.
I fixed his computer.
Oh, thank you.
When I get a gold star.
I'll give you a gold star later, but what I do want to remind you all of is slope is equal to, we said the change in y divided by the change in x, right? So if you have the slope for this line, which is the change in the distance divided by the change in the time, distance divided by time is what? Is what value? Speed. Okay? So that's what I want you to understand here, is the slope, in this case, for this type of graph, equals speed. All right? So whatever the slope of the line is, that's how fast the object is moving. Therefore, if there's a bigger slope, that means a greater speed. Right? If there's no slope, like in the first graph, there's no speed. Right? Okay. Now we're getting somewhere. So let's take a look at this. Look at these questions. You have a position and distance. You can say it both ways, right? Because if the position is changing, then that's indicating the distance. That's not a big deal. Don't worry about that. But when you see this, you see kind of things a little bit different, or are going on here that are different, right? So this would indicate that there's change going on with the object, right? So again, just kind of giving you an idea of things that you're going to have to be able to do is to look at a graph like this and say, okay, what's going on at these different time intervals? Right? Okay. Let's answer some of these questions. So what is the object doing between 2 seconds and 4 seconds? Huh? No. No, we got lots of time. Yeah. Okay, good. So between 2 seconds and 4 seconds, right? It is moving forward. Okay. I like to be super concise with my words, and we have 2 words there, and both of them mean something significant. One says it's moving. How do we know that it's moving? Because there's a slope, right? The slope's not 0, so this object must be moving. Now, the second is, what is the velocity during that interval? Don't get stressed out, velocity or speed. All you're going to do, well, what are you going to do? How can you find that? How can you find this velocity / speed from 2 seconds to 4 seconds? Huh?
Oh, you can look at the number 3, like from 2 to 4 on the x-axis.
Right? And look at in math class, they'd be really happy if you say this word starts with an S. Slope. Right? Get the slope of the line between 2 and 4 seconds. All right? So, got it? So let's do this. Between 2 and 4 seconds, right? You want to do y2 minus y1. We'll just do this out here to make sure that we all see this, including the ladies at home. All right, so at y2, so that y here, what's y at 4 seconds?
I just have a suggestion. You should get like gold stars.
I could. I should get a list.
No, and then we can get stickers.
No, I would wear that. I would wear that with pride.
And then you can get like red stars when we're bad.
I might.
What?
I might. That's not a bad idea. I'll have to think about that. But regardless,
I'll buy them for you.
regardless, at 4 seconds, what is our y value?
It is 54.
Good. 54 meters. And what is our y1 value, our y at 2 seconds? 16? Okay. So then x2 would be 4 seconds, and x1 would be 2 seconds. Right? Okay. So what's 54 minus 16? 38? Meters divided by 2 seconds, or 17 meters per second, right? And notice it is positive. So a positive speed means that it's moving forward. Right? So again, going back to our Liz example, if we have Liz moving to the office, a positive speed would mean that she's going towards the office. Yeah, I did. That's what it is. Now, yes.
What if it was a negative?
Okay. Well, if positive speed is Liz going to the office, what would negative be? Liz coming back.
Why is that negative? That'd be positive.
Because
Well,
you're getting closer to the original.
Okay, now, psychologically for the class, it would be positive because you're coming back. However, physically, it would be negative because your distance, your position is decreasing. Okay? Okay, so we got 17 meters per second and it's moving forward. Okay, now, so let's say this is actually Liz, then what would she be doing between 6 and 7 seconds?
Is Liz your favorite?
Yeah, this is good.
At rest.
Right? So that's maybe she's at the office and she's waiting to get her the medication, right? So she went to the office. She speeds up when she stands up. She's walking, and then she rests here, waiting to get the
Is there a
medication.
meeting going on for 60
There might be a meeting. I don't know. I don't know why she has to wait for 3 seconds or 2 seconds there. But so, okay. So since that's the case, and we'll say at rest. And what is the velocity during that interval? Now, logically, what is the velocity? Yes. 0. Okay, but we can even do it mathematically and say, okay, 72. The slope is 72 meters minus 72 meters in the second position. All right. And then that's 7 seconds minus 6 seconds. So either way, we're going to get 0 over 1, which is obviously a speed of 0. Right?
I have a question.
Yes.
So, like, for Anna and Marissa, we're like on FaceTime with you, basically.
What I'm doing is I'm recording the class, and then I upload it to YouTube, so then they can watch it when they have time. And
Is it like
Someone got a channel now? I gotta subscribe.
Bruh.
The Chiller. Make sure to turn on post notifications too.
all right, should I end all my videos with like and subscribe? Put on the notification bell.
Like at 5 million subscribers right now.
All right.
Bro, I need to delete
Well, maybe I'll give you the channel and then you can look. I think there's even videos of my cats on there, so whatever. All right. So it's not that exciting, trust me. Now, my name is Scott, yes. Now, listen, let's get through this. So, what is the object doing between 8 seconds and 10 seconds? Okay, so again, if we're going back to the Liz situation, what's she doing? She's coming back, right? Okay, so let me say moving backwards. Mapping. Moving backwards. And the slope then would be, okay, so then what is y2? Oops. What's the value for y2? So that would be the 10-second distance. About 40, 42, something like that. And then what is y1? Not quite. Be about 60-ish. So there's 3 boxes there between 54 and 72. So that's 18. So that would be 6 minus that. So 66 meters. Okay. And then this would be 10 seconds minus 8 seconds. All right. So 2 seconds on the bottom. What's on the top? 42 minus 66. What's 42 minus 66? Negative 24. Okay. So then that's going to be a negative 12 meters per second. Now, notice the negative sign there, right? All that's telling you is that the object is going back to the starting point rather than moving forward. Right? But still, the value would be the same, right? It would be 12 meters per second, although it looks like she was moving faster to the office than coming back. More excited to go to the office than coming back here. Fine, whatever. But any questions on that? All right. Now we made it through that easy enough. We're just going to hit the first little bit of this. Okay. Now, what this is an introduction to the idea of acceleration, and acceleration by looking at the graphs.
I subscribe.
Thank you. I'm glad you found it. Now, so what is acceleration? Yeah, go ahead. Speeding up, right? Right now. All right. I think it's that almost a universal thing that you always cringe when you hear your own voices recording.
It is.
But ideally, and here we're going to think of acceleration as a change in speed. Or actually, I'm sorry, a change in velocity. And we're going to get into the details of acceleration next class. However, we do need to look at this in terms of how we see this on the graph, right? Now, here is kind of a summary. This kind of summarizes what happened with the last set of notes that we just did. All right, if you have a speed is constant, you got a slope constant, it's a straight line, right? If the speed is changing, that's a big point, right? You see here how you have that curved line whether it's curved up or curved down, right? That's a change in the speed. That's a change in the slope. And if you look back at, just real quick, back at the other one we just did, right? You can see that change here, right? Which makes sense because this is when someone's starting off. You know, they're not at top speed on the first step that they take. They have to speed up, whether they're running or walking, to get to their speed. So they're always going to have some acceleration to get to that constant rate of movement. And then when they're about to stop, they got to slow down. Okay? So whenever you see these curves, that means the speed is changing when it's on a distance versus time graph. And the upward curve means that it's speeding up, and the downward curve means that it's slowing down. Okay? Now, going back to this. There we go. All right. So, again, and this is just those points to make sure that everyone is following along. I would, if I were you, I know we talked about gold stars for good behavior. Maybe we have a nice little red star for know this. Okay? Make sure that you understand those points. And given the opportunity, when you get a graph, that you can say, okay, on this line is doing this, it's speeding up here, has a constant rate of speed here, it's at rest here, those sorts of things. Because you could think, okay, those are great questions on a quiz, yes. And what interval above is the object at rest? Boom. Very easy. All right? So make sure that you can do that. No surprises. All right? And we'll go down to here. Now, what I want you to do, I know that we have quite a bit of time left, but that's okay. Where was I? Oh, yeah. For homework, you have, there's 3 handouts, so I'm giving you quite a bit of time because you have quite a bit of homework to do. Yes, it's on 929 in the homework section. Okay? Now, even though I know, for at least for some of you today, seems to be really hard, I want you to make sure, okay, everyone say goodbye to the girls. We're going to shut it down now. Bye. See you next time. Bye.